In this lesson, we'll discuss angular velocity and linear velocity and learn how to calculate both. I want to start with a brief introduction, and it won't last more than a minute. The angular velocity, which we denote using the lowercase omega, of an object moving along a circular path is the amount of rotation in radians of the object per unit time and is given by the formula omega is equal to theta over t. The linear velocity v of an object moving along a circular path is the distance traveled by the object, s, per unit time t, and is given by this formula, v is equal to s over t. And you can find information about s by taking the radius and multiplying it to theta, which is given in radians. Given what was said, if the angular velocity of an object is moving along a circular path of a radius r, then the linear velocity v is given by this formula. So let's keep that in mind as we answer the 4 questions that I've prepared. In question number 1, they ask, determine the angular velocity and the linear velocity of a point on the equator of the Earth. Assume that the radius of the Earth at the equator is 3,963 miles. They are asking for 2 things, the angular velocity and the linear velocity. Take a look at the angular velocity. To calculate that, we need theta and we need the time. One complete rotation of the Earth occurs when t is equal to 24 hours. And picking any point along the equator, within a 24-hour period, it will rotate 360 degrees. But remember, we can't use degrees. 360 degrees to radians is 2 pi radians. Given this information, we can easily find out the angular velocity. I'll write down omega is equal to 2 pi over 24. And this reduces down to 1 over 12 pi. You can even go a step further and say that this is radians per hour. Now let's try calculating the linear velocity. The linear velocity is given by this formula, and we need the value of s, which is given by r times theta. We already know what theta is. We determined that to be 2 pi. So we'll multiply 2 pi with the radius, which given by the question is 3,963. So I'll calculate s first as 3,963, our radius, times 2 pi, and we'll take that product and divide it by time t, which is 24. Let me show you the work below. So I have v is equal to 3,963 times 2 pi over t, which is 24. Now let's use our calculator to help us out. 3,963 times 2, ignore the pi for a moment, divided by 24. The answer is given as a fraction, but changing this into decimal, we get the following, and we'll multiply that by pi, where we get roughly 1,037.5. Rounding this to the nearest whole, the answer is 1038. And let's use the appropriate units. Miles per hour. Just think about that for a moment. If you're located at the equator, every hour the Earth has spun roughly 1,038 miles and you didn't even feel a thing. Let's move on to question 2. The propeller of a small airplane is rotating 1,500 revolutions per minute. Find the angular velocity of the propeller in radians per minute. Okay, so the formula is omega is equal to theta over t. Omega cannot be in revolutions per minute. We need to convert that. We need to convert revolutions into radians. 1 revolution is equal to 2 pi radians. So I'll take 1,500 revs per 1 minute and use this conversion ratio where I have 2 pi radians at the top and 1 rev at the bottom. That will cancel out, leaving us with radians per minute. Multiplying these out, you end up with 3,000 pi radians per minute. And guess what? That's the answer. We have the angle at the top and the time at the bottom, and angular velocity is radians per unit time. And that's exactly what we found. Now, if you'd like some more challenging problems, make sure that you watch part 2 of this lesson, where we discuss more of the relationship between angular velocity and linear velocity. Hope to see you soon.